All right, now that we've got our energy coming into the earth through the sun, we got to do something with all that energy. And that is where heat and temperature relate to the atmospheric circulation. And that's what we're going to talk about this week. We're basically going to be discussing a lot about temperature and how it changes across the earth. So, with that, let's see where we go here. So, what are some of the causes of heat transfer? So, first, we got to define some terms here. Temperature. Temperature is proportional to the kinetic energy of the atoms or molecules. What's that mean? Well, every atom and molecule is moving a little bit. And that motion is kinetic energy. The more they move, the higher the temperature, the more the kinetic energy. So think about a solid that's totally not moving. It's probably very cold, like ice. Maybe doesn't have much motion to it. That's kinetic energy would be fairly low. There are other energies that are a part of atoms. There's the potential energy there as well. And that's the internal energy for those atoms or for that little parcel of air. We're more interested in the temperature, the kinetic energy. The heat is basically energy in transport. What does that mean? Well, it's when energy is moving from one substance to another or from one location to another. It can be done through temperature gradients. If you look at it, we've had cold fronts passing Ohio in the last several days. There are temperature changes that go on with that. And the temperature gets much, and when the warm front comes up, it gets warmer. That's a temperature gradient that's moving through the area. So the second law of thermodynamics basically says heat flows in response to that gradient. It'll always go towards lower temperature to eliminate the gradient. One of the interesting things about the atmosphere is it hates any kind of temperature, pressure gradients, any gradients whatsoever. It is always going to try to work to eliminate them. So in this case, if you have something that is very hot, that heat will always move towards something that's colder, towards ice, for example. So how does heat flow? It can do it by radiation, which we talked a lot about last week. Conduction, when your hand touches something, convection, or even latent heat. The only element that changes phase in the atmosphere is water, and that causes latent heat. So last week we discussed radiation. It converts electromagnetic energy to heat when it's absorbed. Conduction. Think about in the summertime, black pavement, black top of a car, or even black seats in a car, how hot they are when you sit on them or touch them. That's conduction. They've absorbed the energy from the solar radiation, and then you sit them on them, and you get conduction. Heat's trying to transfer from that hot surface to you being cooler. And some things conduct pretty well, like copper, even aluminum. However, air is not a very good conductor. That's why it's used in insulation. When you put insulation in your house, there's air pockets there. That keeps the heat from being conducted through those air pockets, so it kind of protects your house, keeps it the same temperature. It doesn't require as much energy to heat it or cool it. Convection is another one. Think about it in your boiling water. You ever watch the little bubbles come up in the water? That's convection. It can occur in a liquid or a gas, so it occurs in the atmosphere. And when you're looking at it, basically warm air is being sent upwards, pulling heat with it. As it cools, it flows back down towards the earth and then just repeats the process. So when you add conduction and convection together, you get something called sensible heating. And that is one component of how heat is transferred in the atmosphere. The other one is basically latent heat. Latent heat means you change of state for water. The latent heat of water is really a lot. It takes a lot of energy to cause it to change states. If you try to heat the ocean up with the sun in the summertime, it takes a while for that water temperature to warm up. I know here by me, for example, in the winter, right now, temperatures are in the low 40s of water temperature here. And we'll start getting sunshine in March and April. That's up in the 60s and 70s. but the water temperature will still only be in the 50s. It takes months to literally warm that water temperature up. So when you're warming water, changing it toward a gas, you're adding heat to the water to make it a gas. Or if you're melting snow, you're adding heat to the snow to melt it into phase, into water. So think about it. Solid, there's not much molecular motion. Liquid is a little more, and water is more molecular motion. If it goes the other way, if you go from water vapor to a liquid, condensation occurs, and you've gone to a state that doesn't require as much heat. Heat is actually released into the atmosphere. So it actually warms the air when water vapor condenses. And if you freeze something in the atmosphere, it actually warms it more. So something interesting about what happens in the change of state of liquids. So they really have an influence on maritime climates and continental climates. You don't have a lot of water by you, but I'll bet you if you go up by Lake Erie in the mid-spring or late spring, it's a lot cooler down towards Mount Vernon, away from the water. The same impact around here when I go across the bridges and tunnels that are pretty long around here, 6-8 miles sometimes. The middle of that area of water in the spring is quite cool. Oh yeah, in the fall, it's the opposite. It's warmer than the area land. Think about radiation. Radiation comes in. We talked about this last week. And about 47% of the radiation is absorbed by the surface of the Earth. The rest is either reflected or absorbed in the atmosphere. And you can see how complex just looking at this table is. So heat transfers through conduction and convection, and you can see it in cumulus clouds. And then you can add sensible heating in because maybe there's water vapor that is converting to a liquid, so it released heat as well to add more heat to the fire. When you look at the whole Earth as a whole, there's excess of heat that's absorbed between about 35 degrees north and south. In that area, it receives more heat than actually the temperature would actually be expected at this time in our Earth. That heat, that surplus, is actually sent by the exchange of air masses, storms, ocean currents, to northern latitudes where it's used to fill in the deficit that occurs. That's an air mass. An air mass is basically just a huge mass of air. Tropical storms, great sources of heat, pulling them northwards. Extratropical storms will bring up heat as well. So this imbalance that occurs because solar radiation doesn't heat the Earth uniformly from top to bottom and north to south and everywhere causes the weather, basically. It is the root cause of all weather on Earth. Say, for example, you looked at a typical day at your house. And we talked about this a couple of weeks ago. We asked you, why does it get hottest in the afternoon at your house? Well, here's the reason. During the day, even though the maximum heating occurs around noon, it continues to heat into the afternoon, mid-afternoon, before infrared radiation from the Earth finally begins to overtake and becomes more than the solar radiation reaching the Earth. Until that happens, solar radiation is going to continue to heat where you are. So it's all depending on how much solar radiation coming in. Say there's clouds, maybe you won't get as much solar radiation, but you're getting some radiation back from the clouds, so you can't cool either during the day as fast necessarily. But it will keep the temperatures a little bit cooler. And at night, it doesn't let infrared radiation back out as quickly. That's why at night you stay warmer when you have cloud cover. Bare surfaces are great for heating up. The deserts, they get really hot during the daytime and really cool at night because they release all that infrared radiation. Snow cover. The more snow cover you have, the higher the albedo, so it keeps temperatures colder. It actually can influence where a low pressure system will go because the temperatures are colder where the snow is, and it may be pushing the low further southward than you might expect. One of the interesting things is urban heat islands. A few years ago, they did this experiment in Washington, D.C. I've seen done similar in St. Louis and Chicago, where it is much, much warmer. For example, where it's very populated and there's no vegetation. Where it's cooler is where there's rivers or lakes or a little bit more vegetation, a little bit less vegetation there. So it can really make a big difference. With that, I just wanted to show you a couple things, real time. All right, we talk about low pressure systems bringing up warm air. Well, here's the temperatures down in Texas today. It's 58, 67 by the Gulf Coast. And yet north of that low is 24. So the low pushing all that warm air northward to try to influence this cold air up here. And that cold air is over you as well. If you want to look at an air mass, a great place to look at air masses is up in Canada for many times. You look at this big high pressure over Hudson Bay, and the temperatures over this whole area are below zero, running anywhere from about -8 to -12. But it's pretty uniform. This whole area is very, very, very cold. Why is that? Well, not getting much sunshine, a good snow cover probably. So it has a lot of infrared radiation it's losing. So it becomes very, very cold there. And that type of air mass then eventually moves down. And you can see it's come down across the eastern part of the United States here already. And there'll be another one coming later that'll push in more cold air. So now the other area that has very warm, moist air would be over the southeast Atlantic, for example, the Caribbean. The water temperatures there a lot of times are in the 70s and 80s. Warms the air above them, and lots of moisture there. So that's an air mass area as well. And I wanted to show you some temperature gradients here. We'll just look at it today in a morning sounding. The dashed lines are temperature. It's kind of confusing. But if you looked over New England here, at this time, at this elevation, and it's 925 millibars, which is not that far off the surface, maybe a couple thousand feet, you can see there's a very tight temperature gradient across the water there, just off of New England. What goes off the water there is right out in here is the Gulf Stream. That temperature gradient is caused from all this Arctic air. You saw the cold air up here to the north being pushed down, and the very warm ocean. So these air masses, while they form up here, they modify when they move other areas, especially areas that don't have snow cover, which would be in the Atlantic Ocean. So this is just some examples of how what you're learning this week can be applied in the real atmosphere. So please don't hesitate to let me know if you have any questions about this.